Hey, yo, early birds. What's up, what's up? Just gonna set a couple things up here. How's it going? Yo, Blue, yo, Polaris. And copy the tags. No. All right. Let's continue. So I did a little bit off stream because yeah, I thought that it's probably better if I just try to solve the issue and off stream instead of getting frustrated and all that, and and just show the solution here. So what I did was that I tried. So okay, what the problem we had was that if I run this now, I can show you that it works now. So if I click here, it shoots it shoots a ray out, and then I'm showing like each step of the way of this like process here. So first, it's reaching like, yeah, I think it's reaching this one, which is kind of weird. It should be. I thought it was gonna reach this one, so I'm actually a little bit confused there. Why it stops? Why it goes like only to this line? But okay. Yeah, I'm not sure because I think this is the root line here, so it should go to the root line. Maybe. Oh wait, no, yeah. Sorry, this does make sense because there's a plane here that splits the whole world, so the intersection ray has to split with that plane. Yeah, so it does make sense. It does make sense. Yeah, it's just that the sequence that we're seeing here is not exactly the sequence necessarily that is taken. That is like the path that the code is taking. It's just a result of how this algorithm works. So we get like 3 different rays split. Well, the array is like split up in 3 here, and the first one is then it's gray. The line is gray, so that means it didn't. There's no. It was basically inside an empty node, so no intersection there. And the next one we can't really see, but it's also gray. And then the last one, it's inside a solid. So that means that we'll take the start position as the intersection point. So you can see here that we actually get the correct intersection point here along this wall. So that's pretty cool. Yeah. First time doing something like that, and of course if we aim over here we don't actually get an intersection, but we still see the process here where the ray is kind of moving along all these different nodes, and then in the end it like is in an empty node there. Making a game or what? No, we're learning about like BSP. So I'm showing here like how BSP now is used to be able to find the intersection point into a solid by using the BSP. So if you see the red dot, whenever I click, there's a red dot appearing. The red dot is like the intersection point on the solid. So yeah, we're using BSP now to get this intersection point. So that's cool. Yeah, and I guess if we were to add like objects, we could figure out which leaf the object is in. If they're like, we could probably like assign objects into the leaves, perhaps. Now, the objects might have like geometry, so they might have like, you know, it could be a rectangle or a capsule or whatever. So they might exist in multiple nodes, multiple leaves. But in theory, if we know that an object is in a leaf, let's say, we could probably just you know, go through all those objects, like do a brute force collision detection on the objects in a leaf. Yeah, so that's cool. I mean, that kind of continues the idea of using BSPs. I guess the next step would probably want to be something like, can the player move through, like blocking, making so that the player can't move through these walls here. It's bright today. Alright, so I also have this log out here to kind of show the path of the code while I was debugging here. And also, yeah, I'll show you the solution, because we had so much trouble. The error was actually the building of the BSP tree. So for some reason, when I was following this guide, I had to flip some of the signs. I couldn't follow the guide exactly. I had to flip some of the signs to make the maths work, basically. So in the end, it was here when a wall was completely behind or completely in front of a plane, we added them either to the front or back of the plane. The problem was that this was flipped, this was like the other way around. But when I was using the guide, and in the guide it says front segments here and back segments here, but there is some weird, like, I don't know, axis flip going on, which makes it so that we have to add the back segments here and front segments here, and that fixed the whole issue. Then everything just suddenly worked. So yeah, so that's that. I want to add like a very rudimentary thing here. Let's see. Also, let's not show this intersection thing. So now when we like, oops, run this, we won't see. Yeah, we just see the hit thing there. I guess we can do this. We can say hit cube it's at, and it's F64. If we have a hit cube, and if hit cube ends at is more than t, Then we draw. When we set the hit cube, we set hit cube ends at t+1. So it shows for like 1 second and then it disappears, basically. Unless we click again, which makes it disappear. It's just to have it shown there so we can see where we're shooting at, maybe. Make it a little bit smaller, maybe. All right. So, now I want to cast array from the player to see if the player should stop moving, basically. Now we don't really have velocity right now, I don't think. We just move the camera like this. And I guess, I mean, if we want to do this for real, we probably want to have like a full-on physics engine instead of doing this. But I mean, we're trying to use BSPs here, so like if you want to make an actual game, you probably want to use like a physics engine, but let's just do velocity, maybe. And acceleration. And so if we move forwards, we want to increase our, we want to accelerate. No. We want to say, no wait, self acceleration is oh yeah, because now I need D. There we go. Instead of position. Space, whatever. Space can be the same thing. It's just a debugging thing anyway. Okay, so now we have the acceleration. At the end, we're gonna say camera, no, acceleration is equal acceleration add, no, wait, velocity is equal to velocity add acceleration times dt, and then camera position, whoops, is equal to camera position add velocity times, well, we have to, I guess, yeah, I forgot, we have to dot scale dt, there we go. And if we try this, we get a compiler error. get another compiler. This should be 0. Okay, there we go. And another thing is that at the start, acceleration should be set to 0. Actually, it should be set to gravity, but we don't really have a notion of gravity. Yeah, we're accelerating really slow. But we are accelerating, and once we have some speed, I release the button and we get velocity. So that looks good. Now we can increase the speed a little bit to increase our acceleration. Probably need a lot more. Okay, that's more like it. But yeah, now it feels more like we're like in space, which is kind of cool as well. I mean, you have what was that called? Descent, the game where you fly around in space. Actually, I've never played it, so I don't know if it actually plays like this. Maybe it has more friction in space, fake friction. But yeah, this is essentially no friction here. So, and also it's a little bit sliding. We probably want to increase acceleration a bit more. And then cap velocity. Clamp the magnitude. Oh. So let's do like yeah. I don't really know what we would pick here. Probably 1,000. I don't know. Okay, maybe a bit too much. Let's try 10. Okay, yeah. That feels a little bit better. A little bit glidey. I don't know. But, you know, you can mess around with these parameters. And then, so that's that. Now, now we also want to have like friction as well. And friction is a bit weird. One way, maybe we could do like scale by 99. Now this, I mean, it is not dependent on time now, so it definitely need to be depending on the time, I think. So maybe something like this. Negative 0.01 times dt. Yeah, that barely does anything. Are we even stopping here? Okay. So you can see we're kind of stopping by ourselves, but it's really glidey. So let's increase this. I guess this could be like friction. Factor, I don't know. Let's try 2. Okay, let's try like 5. Yeah. It also kind of acts a little bit as a dampening of like the max velocity, I think, as well. We could even increase it a little bit. Let's increase it to 10 maybe. Yeah, and you can see now kind of the max velocity went down because of the friction. But we are kind of stopping. Feels better when we stop now. Also, another thing is like if we move like right and left, we get this kind of constant speed here. But if I press 2 buttons, we get double speed. So what we probably want to do is, instead of just setting the acceleration like this, we want to kind of determine maybe like a direction perhaps that we want to move in, depending on the combination of keys. So if, for example, if W is the only key that's down, then we would want to move forwards. But if W and A is down, we want to move, you know, at like in a way. I think what we want to do is we probably want to say, oh, this is also times dt. I see. Maybe that's why. Whatever, that's probably fine. If we set this to 1 instead, or just dt instead of well, actually, let's just set this to 1. And we'll do that calculation afterwards. Because then we can do a normalization of the acceleration, because then now we should have our direction. And we do a normalization. So over here, we would say acceleration is equal to acceleration normalize. And then we scale that by speed times dt. And that should now be good. Hopefully. Yeah, so if I press, like, if I go diagonal, it should have kind of the same speed. So how long does it take? So about 3 seconds. Yeah, about the same time. Very scientific measurement there. I was counting there. Okay, cool. So now we got our little kind of basic movements here. And what do we want to do? Yeah, so I want to also, like, if we collide with the wall, was the whole thing that we started with here. But I wanted to have these things because of if the wall is stopping us, we should like set velocity to 0, which will become a problem because we're gonna get stuck on the wall basically. But let's start there and we can see how we can improve it. Oops. So I want to remove these. Debug. All right. Where are we? Don't need this. And that's wrong. This one we could move like into debug, draw, intersection info. Wait. What's happening here? Oh, right. This one. Segments. So we need BSP. Let's just put pointers here. Intersection info. Oops. T is get time. There we go. All right. Now, we want to get an intersection point. Maybe after the input. Or maybe before? I don't know, actually. Because it feels like this should happen like in between. Between we calculate the acceleration and velocity and setting the updating the position. Although we could like backtrack, I guess, the position as well. Get intersection point, camera position. Okay, let's do it like this. Let's do camera position. We could do update. This would be like update input. And then we have update physics, which would do this. So input would set acceleration. And other things. Physics would get the acceleration and use that to update position and stuff. No, wait, we need the velocity. Okay, actually, you know what? Maybe we can just give it the BSP so that we can, yeah, the BSP node. I mean, we probably want to update this like this anyway. So we'll get the BSP tree or root. So we'll get the root. And after we've calculated the velocity, we want to do collision get intersection point. Start is position, end is position, add this. So we'll put this to resolve position. We'll get this thing is gonna be resolve position. That's the end. That's the requested position that we want. Start node is root, and then we have intersection info, which we don't really care about, but no. All right, so if we get this intersection point, we get intersection point here. Okay, and then so now we know that we should stop at this point. And even maybe perhaps a little bit before, because the player, I mean, yeah, let's just start at stopping at this point. So we're gonna say that resolve position should now be the intersection point. And that will cause us to kind of get stuck on that point. We could, I mean, if we say, we could backtrack a little bit. So if we If we take the relative position from the intersection point to the result position, so that will be result position subtract intersection point, I believe. Okay, and then we scale that by, maybe not scale. We could normalize it to get 1, and then we scale. Well, let's just take 1 to start with. That will be kind of the radius of the player, and then the intersection point, we would say we would add this point, because then we would move towards the player. We would kind of move back. It's kind of like the intersection point is at the actual wall, but then we move backwards towards the player a little bit, and that is our result position. Hopefully that works. Wait, what's going on? Oh, we're missing. Oh, let's remove this. This would be input, update physics, camera, DSP root. Race. Oh, we need to allocate. Oh, god damn it. You know what? Let's just forget about this intersection info. Let's just say null for that, and then your optional. And you are optional. And then it's like, if we have an info, we do this. All right. Expected to. Oh, right. You can be an error now. All right, let's see now. So hopefully we won't be able to go through. Okay, oh, it's like we're teleporting. Oh yeah, also if we press space, we cannot teleport as well, because the speed was changed. Okay, so I mean, we kinda invented portals. Almost. Well, not really, because it has to be like one solid block, but okay. It's kind of like we're moving through the thing. Maybe this should be subtract then? I thought it would be add, because it should go from the intersection point to the result position. So that's why I thought it was add. But maybe it's subtract? I guess we'll try it. Okay, I see what's going on. So also, like we're going back a little bit. I think the result position, maybe we should also add this. We should add 1. So the velocity scale radius is gonna be velocity normalize, and so result position, the ray that we want to cast is like add this with radius v. Whoa. Okay, let's not do that then. Let's forget about this. Let's just do this. We're just getting stuck on the wall. The idea that I was thinking, okay, now we're just stuck. Can we move through? Are we moving at all? No. I can't back out either. So what I was thinking also is like, instead of doing this, was to try to calculate a new velocity as well. That kind of follows along the wall. Question is, how do we do that? So also, this is where we could try to also do the thing with that Quake 3 was, or I say, sorry, not Quake 3, Quake was doing, and that was to build multiple trees in order to get players being able to, or any object be able to like very neatly work with BSP to understand if you're colliding with something or not. We could use the Quake thing, and what they were doing was they were calculating another BSP tree, but the geometry of the level was like scaled up, or it was not scaled up, but it was like extruded, so that all 3D, like all models were like expanded with the same kind of radius that the player was. Now, the problem though is that you have to use, or the problem for me, because I'm not really familiar with it, was to use something called a Minkowski sum or something like that, where it's like you can have any shape, and if you drag it along outside of like an object, the new area that you get is like the midpoint. You trace the midpoint of the object that you're moving around, and that will give you the new geometry of the object in the level. So maybe we can do that. 1 second. Our band, thank you. Okay, so well, for one, I don't really know how to calculate a Minkowski sum, especially with like 3D objects, although we are actually not working with 3D objects. So actually, if we just say that the player is a circle, we could probably, or a rectangle, or I don't know, we could probably just easily calculate how to extrude these things. Maybe it's just a matter of scaling every object? Question mark? Or not scaling, but like scaling with, not by percentage, but by a flat value. Maybe? So it's like, if we take, so the idea is this: you take the player and you kind of, the Minkowski sum is like moving the player around like this, so that we are always like in contact with this object, and then you trace the center point. This is what I understand. You trace the center point of this object that we're dragging around, and the resulting line is like the new geometry of this thing. But I think what we're gonna do is, I mean, we could simply scale up, like extrude these points from, I guess this would be considered like the center, perhaps. No, that seems it's like when we're here, it's like if we're here, we don't want the thing to move down like this. It's essentially just moving this point outwards like this, but outwards from what? From the center here? What if you have a more complex... geometry? Like what if we did... What if... Whoops. What if we had something like this? I mean, yeah, because we would fit here, but not if... Yeah, we would fit like this. I'm thinking if we could get away with not actually calculating that, but if we have a more simpler shape, maybe we can get away with a more simple equation. Like, how do we even know, whoops, that all of this is going to be considered like one object? And if this, it is, but actually it's not, because the center point is over here, so this would expand upwards like this, which is wrong. It should expand in the direction of where the walls are facing. Maybe that's the key. It's like, but then we actually don't really know if two segments are like connected or not. Right now, I mean, I guess we could maybe we could, or two walls rather. Yeah, because essentially we want to make a new map where all the walls are expanding. I mean, I guess we could try to kind of connect the walls to see that, okay, well, this they share the vertex. Perhaps. And if they share the vertex, we can calculate the angle of where they should expand. So you take this angle and this angle, combine them, it should be down here. You take the halfway point of the angles. Man, I'm just, the way that I'm explaining this, but then this is the same thing here. The angle down, angle left. Yeah, take that thing. I mean, I should probably go and look up how this should be done, but I kind of like, you know, experimenting as well, of course. Yeah, that could maybe work. What if you had like another, like a line like this and another line like this? So you take the midway, which is like straight up, I guess. It looks like. Okay, so in that case, but it's annoying because then we need to know if things are linked together or not. Which I guess would just be how the map is defined. But also another problem that remains is like when we have this BSP, sure, we can see if the player actually collides or not, but how do we modify so that the player won't, like, yeah, the problem still remains with how to calculate that. So if the player is over here and we want to move the player like over here, how do we calculate so that the player slides along the wall? Hello, said who? What's up? What's up? Oops. I can save this file. It's fine. Maybe we'll have this, but we'll just make it like a tiny amount or something. Okay, now we don't get totally stuck anymore, but it doesn't look that great, and we're still like kind of teleporting. We're getting to this point. You can still try to move into Oh, I see what's going on. I think it's the friction, maybe, that makes us move closer. I don't know. No. Oh yeah, we should probably just... Well, I don't want to set the velocity to 0, though. I would like to set the velocity to be something like along the wall. That's the thing. How you doing, said who? What are you up to? So we have the intersection point, we have our own velocity, and then we have the the kind of the angle of the wall. What if we do? What if we project our velocity on against the wall to get the speed at which we should move along the wall, and then we could set our velocity to match the wall direction with that speed. We should get like some kind of factor. I think we should match it against the current velocity. Well, we could probably just use the values is then. Better slept. Yeah. That sucks. I hate it when you're running on like very low steam. No, I'm doing fine. I've eaten a luxurious breakfast and drinking some coffee and learning some BSP a little bit more. I think this is probably gonna be the last stream on actual like BSP stuff, and then I actually don't really know what we'll do, but I am interested in learning more about these kind of game dev techniques. Maybe look into, okay, so if this is BSP, maybe look into how would a more modern algorithm look for this thing. Oh, you're enjoying Solid.js? Okay. Yeah, I'm actually interested in learning that as well. Well, when I want to look into like web dev stuff. Right now I'm in my game dev mode, but how's it going with your Solid.js project then? Okay, so if we collide, I want to take... So the thing is here, like, we only get a point. We don't get the segment. And this is what I wanted to do before. I want to have the segment where we actually collide. So maybe this could be stored in intersection info, actually. Or we could also just return a more interesting object. No, let's just put it in here. Why not? We already have this thing here, so let's add... Maybe, yeah, we'll add a node at where we actually did intersect. should it be the node or the parent node? It's probably going to be the parent node in that case. Yeah, because the node that we intersect is just a it's just a leaf, so we don't get any information there about the segment. It's going well. I just had to change about how to think about things a little, how to manage state. Design is hard, to manage in state is also hard. Okay, but you were the one that was used to native JS stuff more, or and not kind of React? Yeah, because there are some differences in handling state when you're doing things like that. Although I'm not sure how much Solid.js is akin to React, but it has the same kind of friction issues when you go from native JS to React as well. Good morning, HB. What's up? Native JS and HTMX, yeah. But it's also very good to have those basics, because, you know, React and Solid.js all build upon that basic, you know, base. So it's very good to know that. So that's good. First time to do a nice client. The app is client only. Okay, cool. Well, good luck with that. Yeah, let's actually set this to null to begin with. So that should be the parent, which means we also need the parent node here. And when we start, the parent node is just the start node. Here, the parent node is node. And same thing here. Okay, and then if we have an intersection info and we're empty, actually if we're solid, this is where we find the intersection. So here we want to set the node to be the parent node. Okay, so then we get kind of the wall that we are colliding with. So then, now we actually have that here. So let's get our collision, I don't know what to call this, collision scale. And it's gonna be the velocity. Now let's see, the velocity needs to be, okay, we need a couple of things, I think, before we can calculate this. But we basically what we wanna do is we wanna take, see if I can show here. We wanna take the, let's say the player is moving along here, and we're basically moving onto here. So let's say the player is very fast and it like tries to move in here. Okay, now we're again stuck over here, right? So what we're gonna do is we're gonna take this, we're gonna take the player, actually if we do this, we can kind of see this wall has this vector here. Okay, this is the wall vector and this is the velocity vector. So if we take these two, you can see that if we would project the velocity vector onto this wall, it will go down here. We will get some kind of positive number here. If the velocity was like going this way, we would get a negative number, because then we would project like somewhere over here if we had a velocity vector like this. The question is if this is enough to, if we don't want to reposition these or anything. I don't think so. Because if the velocity vector was like this, we're kind of calculating the angle, so then the angle is like 0. So we should stop there. Velocity should be like 0 at that point. But here velocity should be scaled by this number. Or it should be, the magnitude rather should be set to this number. And the angle is going to be set to follow the wall. So I think what we do is we set the angle to be the same as the segment vector angle, and then we normalize the velocity and we scale it by this thing. There might be too many steps. I mean, they might be very unoptimized, but that's what I'm thinking. So collision scale. So let's do, so velocity dot product onto. So now we actually do need intersection info. And we actually need an allocator as well now. So do you have a deinitialize? No. So deinitialize that, so we don't get a bunch of memory leaks, because this is gonna run in a loop over and over. Dot product onto intersection info node, which should exist. I guess if it doesn't, then that's weird. So I'm just gonna unwrap it. Okay, so we got our little collision scale here. And what we're gonna do is we are going to set the velocity to kind of go against the wall. Now the thing is also, we probably want to change the result position maybe. I'm not sure. Let's just start here. And I'm getting like flashbacks to how Doom is like, when you collide in the wall in Doom, is kind of weird. Sometimes you get like stuck. Sometimes you're accelerating because you're on a wall for some reason. Stuff like that's happening. Like if you're moving in like a weird angle, you get stuck. Okay, so that's the collision scale. So now we wanna, what was it? We wanna kind of angle this. What is this? Calculate angle between two vectors? No. I wanna basically rotate. No, I basically just want to set this. So we're gonna set the velocity to be the node segment. Yeah, it is a branch. Splitter vector. And then we normalize that. And then we do... Then we scale that by the collision scale. And I think also then it's like we probably want to use that instead. We don't want to get like the intersection point to be where we want to put our position. We probably want to instead go back and say that result position should be equal to the camera position. Add with velocity again. Scale dt, and that is our new result position. So then really these two doesn't matter. So the intersection point doesn't matter, which is interesting. Okay. Actually, let's do easier to get rid of. Okay, you need... Oh, you don't need allocator, you need allocator. Dot product node branch vector. Okay, we need to turn it into a... Right. We could also normalize it, so... Wall vector is going to be this. And then collision wall 3D. Panic, attempt to use a null value. Okay, fine. So maybe this is wrong. I guess like we could get the node instruction info node or else break to get rid of that issue, but the problem is like maybe it's not populated correctly. Okay. Doesn't seem to do anything now. Yeah. Okay. Strange. Because it should go in here and set the parent. Did I not put the thing in here? Oh, we still say we don't give it the info. There we go. Okay. Oh wow. Okay, it seems to work here. It feels kind of weird though. Yeah, it only seems to work in like one direction. And it also is kind of weird with the angles. But it kind of works. The usual state of this, of my things. It kind of works. Okay. Why does it only work in like one direction? Because the velocity is set to the wall's direction, which we then normalize. And scale. I was thinking maybe the wall is not the vector I think it is. Maybe it's something to do with the parent. That doesn't always work out. Because my thinking is that if you're, the array always stops at a leaf, and a leaf doesn't have information about the wall, it's the parent that has information about the wall. So you have to go out to the parent to look for the wall information. So that's why that is like that. It's curious though why it would work. Also, I kind of understand why we're kind of gliding like that as well, because we're velocity. Like if you stop and try to like move towards another place, the way, like if we try like this, well, okay, we have to be on this side. So if I move here, you can see we're moving on this side. Also, there's like a huge teleporting. Oh, it kind of coincides with the other segment there. So that also is kind of weird. But yeah, as you can see, I'm aiming over here, so we're moving over there. Now we're moving over here, and it works. However, if you quickly try to do it, it's still. I'm always pressing forwards, like it still moves us in the same direction. Also, if I try to, I go on here, on here, and I try to move in like either way like this, it always points me in the same direction. So I think the issue is that we have a we have a small velocity into that direction, which makes it so that it picks that kind of direction instead of taking our acceleration into account, like the point we're moving forwards, because that only slightly adjusts the velocity based on where we point, based on our acceleration. When we accelerate this way, it's not enough to kind of overcome the velocity in that direction. There's like a slight thing happening there. But we probably want to solve this in a more robust way. It's just I don't really know how. I mean, obviously, as I said before, like we probably, if you want to do this for real, you probably just want to import some kind of 3D physics library and use that instead. But this is kind of learning maybe, how you could utilize this old technique to do something like this. Which is kind of interesting to explore this a little bit. But yeah, I mean, I'm learning as well. Like I'm learning how to use, vectors and how to think about these different calculations and stuff like that. So I think it's nice to go through this a little bit. Would be cool to get this working though. And then I think like next step would be to try, because then we have like the solid objects in like a Wolfenstein 3D-esque map. And what we could do as an extension is to add dynamic objects that kind of move around and like, enemies and stuff like that. And figure out how could we render those, but also how can we check collision against those as well. So that we can like aim and shoot and kill and pick up ammo or something. I don't know. But yeah, I'm just trying to figure out if there's something here that is the issue. I mean, it probably has something to do with this parent thing. I'm just imagining that the parent is always gonna be the correct thing, because the parent, like if we take this thing, so the parent of this leaf, which is the solid one, is this thing here. Oh, I see. But it could have been maybe this side. Ah, yeah. It could have been this side. So how would we know then how to get that information? I was picking like the optimal kind of solution here, although it still doesn't really work that great, but whatever. Yeah, how does this actually work? Like, it would be cool if with the intersection point, if we could get which segment it actually collided with. The issue is just, okay, but how can we calculate that? Or not calculate, but how can we keep track of that and fix that? Because at the end... Oh, maybe it's to do with the split. So for this example here, it's kind of simple actually. It's like we should disregard, this is the root node here, we disregard the root node because both of them are on the backside. And then we disregard this node because both of them are on the backside. We disregard this node because both of them are on the backside. And now we're down to this one, which splits the two in half. Which means that, well, we need to concern ourselves with this one because we might now actually collide with it. So maybe we need to keep track of the last thing that actually did the split. Because if we, let's say we did this instead and then had this one here, I'll just remove this here. So now we get a split there first, and these two are like, doesn't do anything because they are both in like an empty space, empty leaf. But here, now we're on this side and we repeat, but we keep track of this segment because this was the last split. This was the last split. So we go in here and we're considering this node, which we don't care about this, nothing happens here. We don't split over here, so we continue. Now we're concerning this node again, this side we don't care, this side we continue. Now we got this one, again we don't care, this one is empty. Both of the things are in here, and this is where we collide. And so the last split that we had was this one, so that's the one that we should consider, not the parent. Okay, let's try that. So let's go to our collision thing. So I think that this should not be the parent, this should be the last split. And of course, I mean, it could be null, but then it doesn't matter. Then Yeah, let's just not have null, let's just have it so that it actually is something. Actually, you know what, never mind. Let's just put null here, because it does have the destination where we put it is optional, so we could put it there. So this is the last split. And then here we actually don't put this node here. We actually keep the last split because we're not splitting here. But down here we are splitting. So instead of putting last split, we put node here because node is the point in which we did the split. Yeah. So hopefully this will fix the issue. Okay, we still got some weird teleporting issues here. Whoa, and now I can move inside. Okay. Okay, we got some weird issues there, but we now have this working on kind of both sides, or all sides now. Okay, this side is still weird. What the hell? Do you work normally? No, you don't. Okay, there might be some directional issues. Still, but I think we made progress? Question mark? Okay. So what do we do? We could add some debugging information to understand maybe what's going on. What if... I mean, what if we had another... Yeah, this is splitting here. But that doesn't matter. What if we had another line like this, which we split as well? I see. So is that split? But then we should end up with something like this, which also splits this one, and this is the last split. Well, this split doesn't actually resolve in an intersection point because there's no solid here, while this split does resolve in an intersection point because this will ultimately do that, which will keep track of this split. So I don't see why that shouldn't work. I mean, with the scenarios that I painted up, maybe, I mean, there might be more other scenarios. And probably there's some weird stuff going on with the velocity calculation as well. So that also might have something to do with it, but yeah. The weird thing is the teleporting. I'm not sure why that is happening. So, I mean, in theory, if you take a velocity, if you take the velocity vector and do a dot product, it should never get more it should never get more, like, the scalar that you get out should never be larger than the magnitude of the vector, right? The scalar that you get out of a dot product should never exceed the magnitude of the first operand. Is that correct? Because it's like if you rotate it all along its circle, it should be maximum its own length. If it aligns perfectly with other vector, it should be like maximum length. If it doesn't, excuse me, then it's some kind of factor. It's some kind of factor between 0 and 1. Now, yeah, it's very strange. I mean, this could be, we could say that this is finished. Like all this bug here, these physics bugs are actually a feature, and we'll make like a game that depends on these features. And players have to kind of explore this weird physics to understand, okay, well, how can I actually move along here? Yeah, I mean, it's really cool. I mean, I've never done anything like this before. Like 3D. Well, it's not really 3D collision here, but it is like we're kind of taking. It's a 3D projection of a 2D map, kind of like Wolfenstein. Although it's lacking a couple things like. Well, actually, Wolfenstein never had a ceiling and floor texture, right? It only had wall textures. And of course we don't have walls. Or I mean, we have walls, but we don't have doors, decorations, items, weapons. But yeah, we do have walls, and we have wall textures, and yeah, we have the intersection point. If you shoot, we know where you are shooting. There you go. But I would like to add to that. I would like to add like dynamic objects as well, so you can shoot. We can detect if you're shooting on an object in a scene as well. Which I have an idea for how we could do that, but I wanna fix this collision thing first. Because it's really strange how this works here. My math is probably all wrong. It sounds good in my head, and when I write it out, or I mean look at the diagrams, but then the actual implementation doesn't work. Yes, when you take the dot product, isn't the first operand is the thing that you project to the other one, right? I am stumped. Yet again. Also, like, I would probably like to do this, because it should be populated. If we get a crash, that means something doesn't really work as it should. Okay, we don't get a crash. No, there we get a crash. Yeah, we should not ever get a crash there. It should always be populated. I'm pretty sure. Okay. I started to get a little bit tired, actually. I feel like my brain juice is like depleting here. You know what? Let's just do this. Let's go and check how did the Wolfenstein 3D collision player collision against walls work? Okay, AI, tell me. Wolfenstein 3D. Excuse me. Used a simplified 2D collision detection system based on its raycasting engine and grid-based map. Oh yeah, they had like grids and stuff. But we could still probably apply something maybe to it. Because the player velocity is still could be any angle. Where the player's 3D movement was translated to 2D map coordinates, the game map was structured as a square grid where each cell was either empty or contained a solid wall. Here's how the wall collision worked. Tile-based collision. Before the player's position was updated to a new set of coordinates, the game checked if the destination cell in the 2D grid was occupied by a wall. If a new position contained a wall, the movement was simply prevented or blocked. Is that true? I mean, I would like more details about exactly how. Player radius and sliding. The player was... Because if it just stops, then you get stuck. You should be able to slide. Okay, well, maybe this is talking about that. The player was not treated as a single point, but as a small invisible circus with a radius. The engine checked if this radius collided with a wall cell. This allowed the player to slide smoothly against walls, rather than getting stuck instantly if they weren't moving perfectly straight. Okay, so somehow they could check a circle radius against the lines as well. I mean, we could do that as well, because you could just use, instead of checking instead of casting a ray, you would check the circle collision with the line instead. And then I guess if you get a split, you have to kind of split the circle somehow. We don't have to split the circle in the same sense though. We could use the same exact circle, I think. Although, how would we get the intersection point? Maybe the intersection point is not actually needed then. We just need to know which wall we're colliding against. The engine checked if this radius collided with the wall cell. This allowed the player to slide smoothly against, along the walls rather than getting stuck instead if they were moving perfectly straight. But how did you calculate that? 2D math check, specifically the engine's try move function, calculated if the player's intended next position would put them in a wall tile. Collision box would give player would given a size. Collision box proximity to 20 pixels. For the players, until 26 for projectiles to prevent them from passing through walls at high speeds. push walls doors. Moving elements like push walls or doors or handles special tiles temporarily became solid or empty during movement. Oh. If you'd like, I can explain how the raycasting rendering created a 3D illusion. No, please. No, thanks. Describe how the engine handles collision with enemies. I have an idea there, so I can. I think if we just solve the issue with the player first, we could probably do the enemies ourselves. Show simplified code example for the triangle function. I mean, I can figure out how to, instead of checking with a ray that moves forward, instead we try a circle. But the problem is still remains, though, to know. So if we could get the wall that we're colliding against, that's what we're trying to do right now. Like, but we're not using a circle, we're just casting a ray. That is like, we're casting a ray towards the wall from the player's center. And the ray is basically the velocity. Maybe the velocity is hang on, did I do something wrong here? So the thing is, the collision scale should already include a DT here, and we also scale by DT here. So it's not like it's going crazy because we forgot DT. I mean, yeah, this feels like one of those things where if I take a break now, it's gonna continue, my brain is gonna continue working on the problem like subconsciously. And then maybe I'll need to sleep on it, and then maybe the next day, hey, we got a solution. Usually, this feels like one of those problems. Okay, I mean, let's just ask AI. So how would you calculate, so given we know the wall that we collided with, how do we calculate the new velocity in Wolfenstein 3D Engine? The sliding effect isn't a complex physics calculation involving force and momentum. Instead, it's a byproduct of axis-independent movement. The engine does not calculate a single combined velocity vector. It treats movement along the y and x axis as two separate sequential checks. The separations... Oh, wait. Oh, I see. And since all of them are aligned on the x or y axis, if you simply move along one of them, you will slide against the wall. But what about the speed? Or would you simply ignore the y-axis? Like if you're colliding into a wall that moves along the x-axis, or it's like it's defined along the x-axis, then you would just cancel the y. You would just cancel the y value. And just keep the x velocity. I mean, that's kind of what I'm trying to do. I'm trying to just calculate this. using vectors instead. Game first attempts to player along the axis. It checks the player collision radius with its sector wall time on the X position. X is place X coordinates updated. Movement for that frame along the axis simply set to 0. Yeah. Sliding catches immediately after the X-axis check. The game performs exact same process for the X for the Y-axis, independent of what happened in the first step. If you're walking diagonally into the north-south wall, the X movement is blocked because it would move you into the wall tile. The Y movement is still allowed because your movement parallel to the wall doesn't enter a wall tile. Yeah, okay. Resulting velocity. The new velocity vector becomes the projection of your original movement vector onto the plane of the wall. See, this is what I'm trying to do. This is what I'm trying to do, but maybe I'm doing something wrong. Mathematically, if your intended velocity is v and the wall's normal, the direction pointing straight out of the wall. See, I also thought correctly there. And your new velocity is v new. Okay, v new equals velocity minus velocity times. No wait, dot product of the velocity against the normal. Is this times multiplied by the normal, or what's going on here? But doesn't my way also work? Like, you, instead of taking the normal, you take the wall itself and just take the dot product of that, because that's what they're saying here. The new velocity effectively becomes the projection of your original movement vector onto the plane of the wall. Like, that's what we're doing. Why are we worrying about the normal here? I guess because the normal, it has like a direction or something. So we take that into account. But our walls also have a direction. That's the thing. Like, they have a direction which should work as well. Like, they're always aligned the same way. Wait, is that always the case though? Maybe we do need the normal calculation. We'll try it. Because Wolfenstein 3D walls are always aligned to a grid, the normal is always a simple unit vector like 1 or -1y. This simplifies the math, just zeroing out one of your velocity vectors. Right. The new velocity is calculated by zeroing out the component perpendicular to the wall, allowing the component parallel to the wall to persist. Oh shit. Why did I not show this? Sorry, I just read all this without showing anything here. But yeah, I've been reading this AI thing. And it did confirm my idea, but I'm maybe doing something wrong. I mean, it kind of confirmed my idea. It's just some of the details are a little bit different. But we'll try this calculation. So it's like the new velocity should be the old velocity minus the old velocity dot product with the normal, and then this times the normal, and that's apparently our new velocity. Okay, so we need to get the normal. Also, why would the node be empty sometimes? But let's just get that back. And you are node. So sometimes it's not actually. So that's the wall, and we need normal is the normal. Let's do velocity 2D instead. Velocity X, velocity Z. Okay. And then the velocity, wait, so new velocity is going to be velocity 2D subtracted with the velocity 2D dot product towards the node normal, and then this is scale or multiplied the hell by the normal wait. Oh. Wait, is it just scale then? So it's like, okay, so it's node normal scaled by the dot product. And then u will be u velocity x 0, u velocity y. Wow. Okay, so now it just works. Okay, good, great. Wait. It almost looked like we moved into the wall, yeah. Okay, so I think it's because of how we kind of check the intersection. Yeah, when you reach like the edge, you can kind of go into the wall. All right. The question though, wait, that also moved into the wall. It's like when you're like exactly in the center, you can go out. Okay, I mean, it works a lot better. Man. But yeah, okay, so, I mean, essentially, we're just trying to see... We don't intersect... So this is casting a ray, okay? What if we added a function that checked for a circle instead? So I'm gonna go to the drawing board again. So how would that work? Because let's say we have a circle here. I mean, let's just use the player. Oops. No. So of course, trivial example here is like if the circle doesn't intersect with anything here, it basically just, it's on this side, so it doesn't do anything. If we're on this side, it's kind of it's the same idea with the ray. We are on this side entirely, so I mean, yeah, if we don't intersect and the point is like in front, we are on this side, so we check there. If we're on this side, we check the back side, and so on, until we are at the leaf, which is this leaf here. And then it's the same thing. If we're at the leaf, we know that the whole circle is supposed to be in the leaf, right? So if it's empty, there's no intersection. However, what if we're over here? I guess the intersection, like, I mean, we don't really have an intersection point, so it wouldn't be the same kind of calculation. I guess it would be the same thing that we're trying to do, otherwise it's like getting the last split. So we're looking at the last split, which in this case we don't really have a split. So if we're in here, it doesn't really make sense. Like, you know that we're in a solid, but we're not actually colliding with anything. We're not colliding with any walls. But if we're over here, this is the most trivial example, I would say, because we're not colliding with this one, we're not colliding with this one, we're not colliding with this one, so we're at the end of a thing. Like, this node has two children which are leaves. So we're colliding with this one, which means that we need to check both children. But the circle stays the same. So but now this becomes the last split here. And we're checking this child and this child. So it's kind of the same idea as the line, the raycast, but now we don't really have an intersection point. We could technically calculate two intersection points, like one here, along the circle outline. But really, we have the circle and we have the segment. So we're really just interested in saying, like, okay, well, this is a segment that we're actually that we're colliding with, and it's a solid wall. Okay. But so now it's kind of the same as the raycast, but there's a difference. Because we can have a situation like this, where now we're technically in like multiple universes here at the same time. So we're both in this, so we're both splitting over here. We have two splits now. We're splitting on this one, but we're also splitting on this one, which for raycast is like kind of impossible that you would have multiple splits, because now we're colliding with both of these walls as well. So it's a little bit different. So how would this be? We would go to the root node and see that, okay, we're splitting here. So we have this split. This side is an empty leaf, because I'm ignoring these walls over here right now, and they are not part of the map right now. So this won't end up in a collision here, so that's fine. Then we're on this side over here, so this will, I'm jumping a few steps ahead just to speed up things here, but this side will also say, well, actually first we're on this node here. This node, we have an intersection, so we split again. So I'm gonna say that maybe when we have an area and not a point that we're trying to find, if we have an area, we probably want to have like a number of different splits, so we could probably keep track of all the segments that we collided with, maybe. But then the problem becomes, how then would we calculate how to collide against these walls, is the question then. And if we look at, again, if we look at the Quake, how Quake did it, Quake were using multiple BSP trees where the map was extruded and then used raycast on the extruded tree to find collisions. But I feel like that, like I'm not really sure how to do that. So maybe we could do something simple like this to try and, but what would we do with multiple segments though? Maybe we try to align against both somehow. Like let's say we are over here, we're trying to move like into the wall like this. I mean, we don't even need these diagrams. We can just do this. So we're trying to move in here. So if we're in here, it's obvious that we're choosing this one because that's the only one that we're colliding with. But we're over here. We are going to get two segments that we're colliding against. We could So if we're moving up like this, if we choose to adjust the collision against this wall first, we would kind of end up like this. And then this wall, we would end up like this. So if we would move up here, we would teleport over here. I mean, okay, maybe we do a raycast as well. We check both the circle and a raycast. The raycast will tell us which segment we are like actually colliding into, maybe. And then we'll just pick that. That could allow us to say that, okay, well, this is the segment we should worry about right now. If we come from here, then this would be the segment that we're trying to move into. If we come at exactly this point over here, I guess we'll just pick one over the other. That could be a way to solve it. So we would essentially need to do two traversals to be able to do this, I think. But here's another issue. What if you had like a bunch of walls like this? And you like move through here. So essentially what I'm trying to say is that we're colliding against this wall, and this wall. So those are three different walls that we're colliding at the same time, and we need to adjust our position. I mean, or another example would be, would be this. If you had one wall going like this, and then another wall going like this, and then you move along this wall, but then you get up here, now all of a sudden we have two. You're moving along this wall, and then you get up here. The velocity is maybe like, the velocity goes over like this. So this would be the wall that we're concerned with, but we still also want to concern ourselves with this wall as well. So maybe if we take this example here, the velocity goes up like this, so we're colliding with this wall first. Maybe that denotes which wall we should start with aligning. So if we go up like this, it's like aligning. First it's aligning against this wall, and then we're aligning the rest of the walls. Maybe? Because now this doesn't need to align with this wall anymore. Or we don't need to resolve the collision because it's like not colliding anymore. But if we're over here, we're going like this, right? So this moves up here, and now all of a sudden we have to go like this, and here now we're touching two walls. So first we have this velocity vector that we're trying to get, and this will, so now we're resolving, so we're moving like inwards like this, but now we need to resolve this wall. But that will put us over here though, which does not really work. I don't know, man. I mean, okay, what if you could combine the two? Also, like, if we're over here, it doesn't really make sense. No. See, I can kind of make sense of this situation here and try to combine the two adjustments to like move over like this. But over here it doesn't make sense, because if you're moving in like this, a combined effort here, this should only take into consider this wall. This wall shouldn't even be in consideration here. Because if we combine the two, it's gonna end up like something like, first, well, this is where we probably would want to be if we're moving like this, and we would stop over here. What if we casted a ray from this point and this point, and then we would do kind of the same thing. We would kind of try to align, if this point collide, no. Okay, I just asked AI here. So, okay, what if you collide with multiple walls? In Wolfenstein 3D, colliding with multiple walls, such as moving directly into a corner, two must meet, is handled by the same axis-independent movement logic. Okay, well, yeah, because it's simplified. What if you didn't have the simplification, though? But okay, let's just read through it here. Because the engine checks the X and Y movement separately and sequentially, it automatically resolves complex collisions without any special multi-wall calculation. Here's now the engine handles a corner collision step by step. Step axis, sequential axis checks. The game doesn't look at your total movement vector all at once. Instead, it runs two distinct tests. Step A takes your intended X movement and checks at new position would overlap a wall tile, set to 0. B is the y-axis, same thing. 2. Result hitting a corner. If you move diagonally into a corner, the x fails and y fails to become 0. Final result, your total velocity becomes 0 and you come to a complete stop. Edge case, sliding between tiles. Because the player has a radius, you can sometimes be touching multiple tiles even if you aren't in a corner. Gap narrower than player. If you try to run through a one tile gap diagonally, the separate axis checks ensure you don't teleport through the corner. If the X or Y step would put your radius circle into a wall, that component of movement is blocked. The sticky corner quirk. In very rare cases, at specific angles, a player would jitter because the X check might pass, but the Y check might then push you back into a position where the X check would have failed. Maybe I should ask about the Doom algorithm because Doom has any angle wall, so it doesn't use the same algorithm here. Okay, now explain how Doom did it. The Doom engine significantly evolved from Wolfenstein 3D by moving away from simple grid to arbitrary geometry, lines at any angle. This required a shift from basic grid cell checking to a more sophisticated system using block maps and line defs. Yes, oh yeah, line defs, that's what it was called. But I'm pretty sure some segments are in there as well. Okay, well, spatial partitioning the block map. Instead of checking every wall in the level, uses a block map, a 2D grid overlaying the entire map. Each grid cell contains a list of every line def, wall segment, and thing that passes through it. Right, so that was also my idea that dynamic objects would be separated into the BSP nodes as well. So this is kind of the same thing, except they are partitioning the space differently by using this block map. I didn't actually know this. I thought they used BSP, but maybe that was for maybe that was for like more modern ports or something like that. When you move, the engine only checks for collisions with objects in your current and immediate neighboring block map cells. Cool. Line-based collision. Because walls can be diagonal, Doom uses vector math to check for collisions. Intersection check. The engine checks where the player's movement path intersects any line def in the relevant block map cells. Radius testing. The player is still treated as a circle, radius 16. The code calculates the distance from the center of the circle to the line def. If the player is within the radius distance of a wall, the move is blocked. Calculating the slide. Unlike Wolfenstein 3D, which just zeroes out an axis, Doom calculates a slide along the wall specific angle. I mean, given the wall sliding in Doom is not really perfect, but at least we could maybe get an idea on how to calculate it at all and get it like somewhat working. Backtrack. If a collision is detected, the engine backtracks the player until they are no longer intersecting the wall. Okay, so I'm going to assume they do a calculation to calculate exactly where to put the player at that point, because doing a bunch of iterative checks would be very difficult resource-wise, I think. Projection. It projects the remaining movement velocity onto the tangent of the wall line. Yes. And that is what I was trying to do as well. Iterative checks. The engine repeats this backtrace slide process up to 3 times per frame. Oh. This allows the player to slide into a second wall after hitting the first, preventing them from getting stuck in tight corners. What? I'm trying to understand. I'm trying to picture and understand this. 3 times per frame. So, I mean, does it check against different walls then, is the idea, or what? Okay. Infamous glitches, the block map bug. If an object's center is on the very edge of a block, it might occasionally miss collision detects with objects in the adjacent blocks, allowing bullets to pass through enemies. Right. Wall running. If a player moves north or east along an axis-aligned wall at high speed, the collision code sometimes fails to split the path correctly, granting a massive speed boost. I think that's what I was trying to say earlier. Player moves north or east along an axis-aligned wall at high speed, the collision code sometimes fails to split the path correctly, granting a massive speed boost. Would you like to know more about the binary spatial positioning tree and how it relates to this collision system? Wait, what? I've never mentioned anything about the BSP in here, I don't think. How did you know about that? Google is listening. Did I say anything about BSPs? I don't think so. Okay. Explain how Quake. Well, I know how Quake did. Well, I know how Quake calculates if we collide or not, but I don't know how it uses that information to calculate how we should slide along the wall. Calculates wall sliding. In Quake, wall collision moved from 2D logic to true 3D continuous collision detection. Because Quake allowed for slope stairs and full 3D movement, it couldn't just zero out an axis like Wolfenstein or project onto a 2D line like Doom. Well, we could probably still do that, but it's like I would like a more robust way as well. It uses a method called recursive vector clipping. The hull and trace. Instead of checking a circle against lines, Quake treats the player as an AABB aligned, axis-aligned bounding box. When you move, essentially a cube or a cuboid. When you move, the engine performs a trace. It calculates swept volume, the path of your box takes from point A to point B. It checks this volume against the map's BSP tree to find the exact. So it's basically like extruding. It's like you're taking a capsule and then you're kind of moving. It's like painting in 3D. You take a capsule as a brush and you move it along while painting along the way, and the result will be the volume that you want to check. I see. Interesting how you would well, if it's an axis-aligned bounding box, it's easier to calculate, I guess. But what if you're moving like at an angle? It checks this volume against the map's BSP tree to find exact point of impact and the surface normal of the plane you hit. Okay, so it actually does find 1 point of impact. But I mean, technically you could get multiple, because you could, if you're moving into a corner, you would hit multiple walls. The clip velocity function. When a trace hits a wall, Quake doesn't just stop you. It calls a function famously named PM_clip velocity in the source code to redirect your momentum. It uses the dot product to find out how much of your velocity is heading into the wall and subtract it. Okay, so that's exactly what I try to do as well. Formula is the new velocity is velocity minus velocity times, or dot product with the normal times the overbounds. Okay, so this is different. Wait, this is a cross product. Wait, but this is a scalar. What does this mean then? The overbounds. This determines the magnitude of velocity directed at the wall. Overbounds. Quake adds a tiny multiplier to the correction. This pushes the player along a fraction of a unit away from the wall to prevent them from getting stuck inside the geometry due to floating point errors. Okay, nice. The recursive loop, multiple walls. This is where Quake gets clever. If you run into a corner, the engine hits wall A, clips your velocity to slide along wall A. Okay. Checks remaining movement. If you still have distance to travel in that frame, it tries to move you with a new clipped velocity. Oh, so it does like 2 physics checks then. If the new path hits another wall, right, so it wouldn't hit the same wall, right. It clips the velocity again against wall B, the crevice fix. If the second clip would send you into back into wall A, right. That was also an issue that we predicted. The engine calculates a new vector along the intersection line of the two planes, the crevice. Okay, what if you have even more walls? But okay. So it tries to do like a fix for that. Interesting. Physics side effects. This specific method was created in Quake's legendary movement. Bunny hopping, strafe jumping, because the clipping math only removes velocity into the wall and doesn't capture speed in other directions. Players discovered they could add speed by jumping and air strafing, essentially tricking the clipping logic into never slowing them down. Floor friction. In Quake, the floor is just a wall pointing up. When you're on the ground, an engine is constantly clipping your gravity-induced downward velocity against the floor plane. Okay. Do you want to see the actual source? Okay. So basically it's just... Okay, so first of all, it does find an intersection point based on the area or volume of the thing. And now we don't really do a trace though, we just... Well, actually we do a ray trace. But how would you trace the circle though? Alright. I think that's gonna be it for this time. My brain is nearing its end of its power right now. 'So, but yeah, I think... it would be cool to get something remotely kind of working here and figure this out. So I'm probably gonna continue with this next time, and probably gonna try to think of solutions to this or do some more research. But yeah, that's going to be it for this time. So hope you have a nice day, and thank you very much for joining me, and I'll see you later.